In this lecture, we will learn about single-order inventory models, also known as Newsvendor models. Just to remind you, our coverage of inventory management started out with a discussion of inventory control methods for known demand. Specifically, we talked about dependent demand models and independent demand models. And then we talked about inventory models for random demand and lead times. Looking at multiple order models first, we explored both periodic review models and continuous review models. We then focused on the latter and learned about the reorder point model in great detail. To round out our coverage of inventory management for random demand and lead times, we want to focus on single order or Newsvendor models. Now you might ask, why is a single order inventory model called a Newsvendor model? Just put yourself in the shoes of a news vendor who operates a kiosk on the busiest street in town. Every day, you will need to make a decision as to how many copies of the newspaper to order for the next day. Keep in mind that you probably won't be able to ask the publisher to print more copies if you see that you're running out of the newspapers by the afternoon. And conversely, if you have leftover copies at the end of the day, you won't be able to sell that inventory the following day. Of course, the Newsvendor model does not apply to newspapers only. Products with a limited shelf life, such as produce or dairy products, face similar constraints in that retailers can keep them in inventory for a limited time only before they perish. Think of fashion items. Lead times in the apparel industry are often greater than 6 months. So retailers need to think about how much swimwear, for example, to order in the fall for next summer season. The store will sell most of their inventory in the summer. However, once the seasons change, hardly anyone will want to buy swimwear anymore. The same can be true for high-tech products. After all, would you want to buy an outdated computer? What all these examples have in common is that there is what we call a finite selling season, beyond which inventory will essentially become obsolete. In addition, there often are limited or no opportunities to replenish. Think of Christmas trees. When a seller runs out of Christmas trees on, say, December 15, they will not have a chance to grow more trees before the end of the season. In other words, there will only be one order placement per season. And that is why we call Newsvendor models single order models. Now that we understand when to apply Newsvendor models, let's figure out how to make optimal Newsvendor inventory decisions. Of course, we know that our objective always is total cost minimization. So then the question is, what costs do we need to minimize in a Newsvendor context? Let's take a quick look back at the reorder point model, which, recall, is a multiple order model where we can hold inventory and place multiple replenishment orders over time. In that case, we were concerned with minimizing holding costs, ordering costs, and backorder costs. Now let's take a look at this from a Newsvendor perspective. Will we be concerned with holding costs? Not really. This is because we will never hold inventory from one selling season to another. If we ordered too many copies of the newspaper, for example, we will overstock and incur a cost of overstocking. This could be the amount we paid to buy the newspaper plus a disposal cost. In the best case scenario, we might be able to sell any leftover newspapers to a recycling company and earn what is called a salvage value. In the reorder point model, we were also concerned with ordering costs, but that is not the case in the Newsvendor model. After all, we only place one order per selling season, So whatever the order cost is, it will have no bearing on the optimal Newsvendor quantity. And then there are backorder costs in the reorder point model. Clearly, there are no backorders in a Newsvendor model. If today's newspaper isn't in stock when a customer comes, you simply won't make the sale. So there is a cost of understocking. And this cost is essentially the profit the Newsvendor stands to lose by missing out on a sale because he or she was out of stock. So long story short, in a Newsvendor context, we are concerned with choosing a Newsvendor quantity so as to minimize the sum of the cost of overstocking and the cost of understocking. By now, you probably know what comes next. We first set up the total cost function. Here we will call this G of Q and D. This is because the grand total cost, G, will be a function of our choice of the order quantity Q and realized demand D. The first component is the cost of overstocking. The cost of overstocking per unit is C sub O, and we multiply this value by the total overstock quantity. Of course, we only overstock if it turns out that Q was greater than realized demand D. Otherwise, there is no overstock cost. The same logic applies to the cost of understocking. C sub U is the understock cost per unit, and the understock quantity is the difference between realized demand D and the order quantity Q. If this difference is positive, there will be a cost of understocking. Now, we will skip a good bit of detail. That is, we now have to look at the expected value of G of Q and D, and this value will be a function of the probability distribution of demand. But we're not interested in integrals and math here, so we'll jump straight ahead to the optimal solution. And this solution is amazingly simple and intuitive. The optimal in-stock probability in a Newsvendor model, denoted f of q star, is simply the ratio of the understock cost per unit and the sum of unit overstock and understock costs. We call this the critical ratio. Now here's why this is so intuitive. Let's say understock costs are greater than overstock costs. For instance, a Newsvendor may forego $1 in profits for every lost sale, while the loss associated with having a leftover copy at the end of the day may be only 50 cents. In this case, the critical ratio will be greater than 50%, which makes sense since we'd rather avoid understocks if they're costlier compared to overstocks. And what if understock and overstock costs are the same? Well, then we're indifferent whether we overstock or understock, and we simply opt for an in-stock probability of 50%. To conclude, let me show you a visual illustration. This is the distribution of demand per selling season. It has a mean of d bar and a standard deviation of sigma sub d. F of q star is the optimal in-stock probability and is equal to the shaded area. As you can see, it takes an order quantity of q star to achieve the desired in-stock probability. In other words, the optimal Newsvendor quantity is equal to the sum of average demand d bar and z standard deviations of demand, where z is the standard normal variate that corresponds to the optimal in-stock probability f of q star. Let's continue to explore the Newsvendor model in more detail in a series of Excel-based exercises and video demonstrations.